Okay, great. So it's a pleasure today to introduce Arjan Cornelissen, who's here for the quick seminar, and actually he's visiting for about 3 weeks. So if you're interested in meeting with him, he's around. His office is just on the main hallway, and please get in touch if you'd like to talk with him while he's here. But it's a pleasure to introduce him. He's done a lot of interesting work related to quantum algorithms, quantum learning, and other kind of topics in quantum information. He's currently at the Simons Institute at Berkeley, and today he's going to tell us about quantum algorithms through graph composition.
Yes, thank you so much for the introduction, and also thank you so much for hosting me for 3 weeks. It's been very nice so far, and I hope that I can interact with all of you for the coming 2.5 weeks that I'm here. So today I'll be talking about quantum algorithms through graph composition, which is actually like the merger of 2 papers that are both on. So essentially the idea of this work was to try to get an understanding of the different techniques that are out there to kind of come up with quantum algorithms, how they relate to one. And so we refer to these techniques to construct quantum algorithms as algorithmic frameworks. So for purpose of this talk, because I thought it would maybe be nice to start with what I mean what a quantum algorithmic framework is. So what's algorithmic framework? So for the purposes of this talk, I'll be considering the following setting, where we have some kind of function, some Boolean function, like a function with Boolean output, and the input of the function are n-bit strings. So the inputs to this function are just strings of n, 0 to 1. And then we assume to have access to this input string through some kind of oracle. And this oracle, what it does is you can give it you can enter j into the oracle and it will tell you whether the xjth bit is 0 or 1. And it does so by computing this in the phase. There's a standard way of inputting bits into a quantum algorithm. This is just as powerful as classically querying single bits, but now you can do this in superposition as well. Right, so this is the setting that we are considering. And now what we want to do is we want to design a quantum algorithm A that computes this function. So what is a quantum algorithm? Well, quantum algorithm is some kind of circuit where you do some unitary and then an oracle call again, then some unitary and an oracle call again, and you kind of iterate this process. You do this a total of t times, and then you do a measurement at the end that results in an output, which is B, which is either 0 or 1. And now what you want to happen is that the probability that the algorithm outputs the function value, so that the probability that B is equal to this function value, you want this to be bigger than 2. So this is what we say that the algorithm computes function f. And what we want to do is we want to design a quantum algorithm that does this, trying to minimize the number of queries that we make. So trying to minimize this parameter t. Right. So this is a bounded error query, a bounded error on the query algorithm. So we refer to this. And now, what is an algorithmic framework? Well, an algorithmic framework is the following way of coming up with a quantum algorithm, which is to first define a different mathematical object, and then take this mathematical object and turn it into quantum algorithm. So this whole technique, this whole methodology, is what we refer to as a framework. So it's maybe a little bit abstract. So maybe let me give you an example to give you some idea of what I mean here. So one such algorithmic framework is the Boolean formula evaluation. And so essentially what you do there is you take your Boolean function and you write it as a Boolean formula. And then what is known is there's a paper from Rijkaard from 2011 who shows that you can take any such Boolean formula and turn it into quantum algorithms or something like this, where the number of queries that you do is going to be square root of the length of this Boolean formula. Right, so this is just to give you an idea of what is quantum algorithmic framework. You take some kind of different mathematical object, in this case, Boolean formula, and then there's some kind of black box technique to turn that into a quantum algorithm. Right, and so here what you can see is that you see some property from the classical object, namely the length of the formula, which tells you how many queries the resulting quantum algorithms can make. Right, so there's a very obvious benefit of algorithmic frameworks. One is that, okay, now you can come up with quantum algorithms without actually knowing how gates and measurements and so on work, right? Because all you need to do to come up with a quantum algorithm is just write down Boolean formula. On the downside, though, obviously, it might not be always possible to get very efficient algorithms from it. So there's some kind of inherent limitation in coming up with them. Any questions? Okay. Right. So these are algorithm frameworks. And so what I wanted to do at the start of this project was to get an overview of all the different frameworks that are out there. So kind of how do all the different frameworks that are available in the literature, how do they kind of relate to one another? And so the first thing that I did is I tried to make like some kind of overview of like the different frameworks that are out there. So all of these boxes here, they all represent like different algorithm frameworks that you can find in the literature. So here's like the Boolean formula evaluation. And so what we just looked at is how you can go from Boolean formula evaluation to one algorithm. But you can see that there's like actually like, there's more known. Like you can take Boolean formula as an instance of the Boolean formula evaluation framework and turn it into like an instance of the ST connectivity framework. Turn that into an instance of the span program framework. Turn that into like an instance of the dual framework, and then turn it into one algorithm. And if you do all this, you kind of recover still the square root, like pretty.
I'd say that it's a different kind of a thing, but what is the relationship between this and Eichhorn's grand unified theory and quantum algorithms?
Sorry,
What's the relationship between this and Eichhorn's grand unified theory of quantum algorithms?
I'm not sure.
Okay. What was it around 2021?
I'm not familiar with that. We can have a chat after to see how this fits in with. But yeah, so it's certainly possible that there are like other boxes out there. Like it's actually true that there are other boxes out there that are not in this picture. But these are kind of like the boxes that I considered in this work, and like kind of find like some kind of relationship. And I want to mention one in particular, which is the unify conquer framework, which is something that originates from here, from Freeze. So yeah, a bunch of authors in the paper are actually nice to see. Right. So these were the connections that were known like before I started working on this. And so what I'm doing in this work is I'm proving a bunch of connections which are represented here. So the first thing I'm doing is I'm introducing the graph composition framework, which is like a new framework with algorithms. But I would say that the main motivation for this graph composition framework is its unifying nature, which are like all these green arrows is like the second thing that I proved, which is like new connections between these frameworks, so how they fit together. So that's kind of like the overview, like how what I did in this work, how it fits in the bigger picture of things. But so yeah, so this is to give an overview of like everything that I did. And then for purposes of this talk, I'm not going to go through all the boxes and explain how everything works. I'm going to focus on like the middle column in this picture. And we're kind of going to traverse this middle column from down to up. So we're going to start with what span programs are, like how that works. Then I'm going to talk a little bit about how graph composition works. After, we'll look a little bit at some examples of the ST connectivity framework. And then finally, I'll show how randomized algorithms fit in all of this. So that's kind of the roadmap of what I'm talking about. Any questions so far? Anything? So obviously, if you have any questions about any of the other boxes, then feel free to comment to come to me, or somewhere in the comment 2.5 weeks. Ask me about how any of it works. All right. So that's an overview of what I did. Now let's get into like more details of what's going on. So to that end, I'm going to start explaining like what span programs are and how this works. So span programs are like one particular framework for coming up with quantum algorithms, right? So they are one particular methodology for first defining like a mathematical object and then black box turning it into quantum algorithm. So I'm first going to explain how this mathematical object looks like. So this mathematical object has 4 ingredients that you need to define. So these 4 things together define a span program. And the first thing that you need to define is a Hilbert space. So I'm keeping like a artistic interpretation of like what this means by drawing this Hilbert space of like that's this circle on the right hand side. And now for every input to your function, so for every like this is bit streams, like for every input to your function, we're going to define like a subspace of the Hilbert space, which represents like that input. And I'm keeping it on the right, it's like the subspace there. The third thing we define is like input independent subspace. This is going to be like some subspace which is completely independent of X, and it can be, like there's no relation between K and H, like they don't have to be orthogonal or whatever, they can be like completely arbitrary. And then the final thing is an initial vector, which is going to be, the only thing we require is that it's orthogonal to this input independent subspace K. So if you define these 4 things, then you define span program. Right. And now what I'm going to say is that this span program computes particular function, like a particular Boolean function, which takes inputs from the domain and maps to 0, 1. And I'm going to say that the function it computes is defined to be 1 whenever it's possible to write this initial vector W0 as a linear combination of something from the input independent subspace and something from the input dependent subspace. Right? So this is the definition of this function f that the span program function. And so if we look at this picture here you can see that we are in positive case because we can take like a vector from h of x and we can take a vector from k. And if we add like both of those together, then we end up W0.
Is there some maybe physical motivation for being interested in this particular function?
Sorry, what's that?
Is there some motivation for being in functions of this form or being interested in functions of this form?
I'll get to that at the end of the slide. That's okay. Right. So this is how we like define the function that the algorithm computes. And now, if we look at like this particular picture here, we have like a positive input, right? And so what we can do in the case when we have a positive input is we can write this decomposition of W0 into h of x and k, and then single out only the vector which is in h of x. We call that like W max. And this we call like the positive witness, right? Because only if such a vector exists, then it kind of witnesses that this is positive. And now what I'm going to define is I'm going to define the W plus, which is like the norm square of the vector. I'm going to define that as a positive witness. Right, so far I'm just defining things like, I'm not really building intuition yet, but
This might be a silly question, but what is a positive vector?
A positive witness is like a vector in h of x, such that the difference between this vector and W0 is a vector in k. Right, so that's a positive witness. So it's kind of like in this picture is represented as this vector. And like there might be multiple of them, but like I'm going to take like if there are multiple of them, like then any such vector would be a positive witness, and then here I would be taking the shortest. Right. So this is in the positive case. And then in the negative case, you can do something similar. And then the picture looks something like this. So in the negative case, think of like W0 can then not be written as a linear combination of k and h of x. So what's going to happen then is that k and h of x, they can somehow like span like this ground thing in this picture. And then your W0 will be somehow like pointing out. And so if that's the case, then it should be possible to find like a vector omega x here, which is orthogonal to both k and h of x, such that the inner product between this will be 1. And I hope that you can see that you can only find such a vector omega x with such that the inner product is 1 if you are in the negative instance, right? Because if your W0 points out, then it's possible to have some non-zero. And so in that case, I'm going to refer to this get omega x as negative witness, and I'm going to look at the negative witness size as the norm squared of that. Right. And then the final thing I'll define is like that the complexity of the span program will be the square root of the maximum of the negative and maximum of the positive. Right. So okay, so far I've just been defining like many things, right? And why have I been defining all this? Well, the reason is that there's this theorem from like this long line of work, which says that there is a quantum algorithm that evaluates this function f using a number of queries, which is on the order of this complexity of the span program. Right. So like somehow you can compute all of these geometrical objects, and they tell you something about how much work the quantum algorithm is to do. And so what I want to do is I want to give you at least a little bit of intuition for what this algorithm is doing. So what the algorithm is doing is the following. Like it starts in the vector W0, and then it will be reflecting through h of x and then through k, right? And it will keep on repeating. Now, if we look at this like in the positive case, what will happen is like if you reflect through h of x and then through k, what will happen is that you end up doing like a rotation in this picture, right? Because if you reflect through two subspaces that are under an angle of one another, you're going to end up rotating. So here, if you keep on doing that, your W0 will start to rotate like this. Whereas in the negative picture, something similar happens. You end up with a rotation on the ground plane. But the component of W0, which is orthogonal to both of these subspaces, it will stay the same. Right. So and it's this thing that the quantum algorithm is known as. It's kind of figuring out, is my entire vector starting to rotate? Or is there like a component of the vector that stays stationary? So this is kind of like the idea of what the quantum algorithm is doing. And so then, okay, so then you have a whole bunch of like analysis to do to figure out, okay, how much work does the algorithm need to do to actually be able to detect this? And that's where all these geometric objects come in, and like how you can figure out like, yeah, how they. Does that make sense?
You probably you want to explain this oracle because it's not like
Right, yeah, that's a good point. So indeed, like the thing that the algorithm needs access to about the input is it needs to be able to reflect through this subspace HX, right? So this is kind of how like this is the oracle that I assume to have access here, right? So this O of X, think of it as being like the reflection through the HX. Right, because like that's also the operation you're doing here when you're reflecting through HX and through K, like yeah, the input dependent operation is going to be that. Right, and then one more thing that I wanted to say is that like you can like if you look at all this, it looks like a very fancy way to come up with quantum algorithm, but actually how useful is it? Well, what we can show is that you for any function like this, you can always come up with a span program that like achieves like the algorithm, like the optimal algorithm out to constants. So it's like if you don't care about like multiplicative constant overhead, then this is one. Or at least you can always find the optimal function. Any questions? All right, so these are span programs. And then like one thing that's nice about span programs is that you can manipulate span programs like in a way like that you can't do so much with like algorithms on the circuit. So I want to highlight two things that you can do with span programs here that like yeah that we'll need in the rest of this talk. So the first thing you can do is you can do scalar multiplication. And essentially what that means is you take like some positive number, and essentially what you're just doing is like rescaling this initial vector W0. And what you end up doing then is like in this rescale with span program, what happens is you end up multiplying like the positive witness size with the constant, but at the same time you're dividing the negative witness with the constant. So somehow you can always do some kind of rebalancing of the positive and negative witnesses. You can always multiply the positive witnesses with something as long as you divide the negative witnesses with the same. And the second thing I want to note is that there exists like a trivial span program, which just simulates doing a single query into your district. So like here, what I want to do is I want to build a span program which just queries like the jth bit of a bit string. And essentially the way you do this is you just define like these four objects to define a span program. And I'm just going to use like a one-dimensional Hilbert space. And I'm just going to include the whole space whenever xj is 1. I'm going to include like just the empty space whenever xj is 0. And then I hope that like you guys can see that if you now like reflect through h of x, it's going to be exactly the same thing as doing this oracle call, like doing this -1 to the power xj to this one image, right? Because like if we reflect through h of x, if xj is 1, we're not doing anything, whereas if xj is 0, we're just adding like a -1. So up to phase, up to global phase, it's the same thing as we're going to oracle call from the beginning. Right, and then like okay, so for the input independent subphase, we take it to be empty and W2 is just 1. Right. And then, okay, you can do the analysis, you can compute all these witness sizes, and what you figure out is the complexity of the span program is exactly 1. So somehow like the intuition carries over there. Like if you want to do one query, you can do the same thing with a span program that has complexity 1. Any questions? Good. Right. Okay, so this is what I wanted to say about the span program. Then next what I want to talk about is a little bit like what this graph composition framework is. So let me talk a little bit about that. So this graph composition is also like a framework, like a quantum algorithm framework, right? So I'll first talk a little bit again about like what this mathematical object is that you need to define, which you can then as a black box turn into a quantum algorithm. And so like the ingredients that you need to define like an instance of the graph composition framework is you first need to define like an undirected graph. And then in this undirected graph, I want to single out 2 nodes which are like the source and target nodes. That's in T. And then finally, what I want to do is on every edge in the graph, I want to associate like the span program to that edge. And I want the domain of each of these span programs to be the same on all of the edges. Right, so here I do a little example from S and FP, and then on every edge, there's a span program. And now, like, if you take any input from this domain, then each of these individual span programs will either be like a positive or negative, right? So this input will be positive or negative for each of these span programs. And now, what graph composition does is it takes all of these small span programs and this graph structure and kind of generate like a bigger span program for this, which computes the following function, which says, okay, if we now take this input X and we look at all the span programs that are positive in the picture, is it then possible to traverse the graph from S to T along edges for which you are positive? Right. So let me say that again. If you take an input, all of these edges will either be positive or negative. I'm going to only consider those that are positive. Is it then possible to go from S to T? Like this is the function that this graph composed span program. Hopefully that makes sense. Right. So this is like intuitively, you can then think about like, you know, what the new function computes. But then the question that you have, of course, is okay, but how efficient would be that new span program, right? Can we also compute these witness sizes for of this new composed span program? Because then we can say something about the efficiency of the graph.
I'm sorry, could you remind me, how do you have a notion of positive and negative for a given span?
Right. So if I take any input from the domain, that input is going to be positive or negative for each of the edges, right? Because like these are all like individual span programs, right?
Yeah.
And so in each of these span programs, this input will be either positive or
Oh, I see. So given,
yeah, exactly. So indeed, like for a given input,
okay,
you're going to get like some configuration, like some of the edges will be positive, some of the edges will be negative.
Yeah.
And then what the new span program computes is whether it's possible to go from S to T along edges for which are positive. Right. Right. So this is what the function computes, but then the question is how efficient is that new computation? So what's the complexity of this new span program? And for that, we need to compute these witness sizes, right? And it turns out that you can compute these witness sizes in a very like direct way. So let's say that we have a positive input. So let's say that all of these green edges are the span programs for which a particular input is positive. Now what I'm going to do is I'm going to put the witness sizes on all of these edges. And then I'm going to compute the effective resistance in this graph between S and T. Right? So this here represents like the effective resistance between S and T, where the individual resistances are the positive witness sizes of the sample. Right. So think back to like your high school physics where you had to do like this effective resistance computations. You had series or parallel resistances in the system, something like that. These things come back in the computation here. And so what I show in this work is not only how to compute like this new span program, but also how like this witness size of the new span program relates to witness size of the individual form. So this for positive instances.
Sorry, maybe just clarifying, like you talk about positive and negative inputs like a couple slides ago about whether or not this vector has like a projection onto
Yeah.
Is that the same thing or is this?
Yeah, exactly. So like if you take here, so like if you take any particular input X and you look at X on this particular span program P1, that input X will be positive for P1 if in span program P1 you can write this W0 as like, you know, the sum of like something in H of X and something in K. But so all of these span programs have their own like vector W0 and their own space K and their own space H, right? And so what this construction does is it kind of like takes all of these individual span programs and kind of merge them together into a much bigger span. And then what I'm saying here is somehow like how you can compute the witness sizes of this new span program from the witness sizes of these individual.
And maybe I just missed it, like, are you going to mention like what is the motivation for it?
Yeah. So I'll get to that after.
Yeah.
do you have any intuition for why it composes like the effective resistance?
Right. Yes. So actually, if you write effective resistance computation, like we don't get taught it like this in high school, but you can phrase effective resistance computation as like a Hilbert space program of computing like the size of the support vector of an affine subspace. So there is like some very, very linear algebraic like interpretation of computing the effective resistance that looks very, very similar to the picture I just drew from the plan program. So there is like a very like natural connection there. Yeah, but like it's just, yeah, we didn't get taught it like that. Like so I think if I were to give a class on effective resistance, I wouldn't start like that too. But yeah.
So, why, I'm really confused why this is an undirected graph rather than being direct.
So indeed, like you can traverse all these edges in whatever way you want.
Yeah, but why do you have that freedom? Like I would assume that so maybe I'm a little confused about what what sort of composition is happening between programs. I would expect that when you compose programs, it's usually a notion of directionality.
Right. So that's indeed very particular. But so somehow like this construction only works in the undirected case. It's actually a very big open question still if you can somehow modify any of this work in the directed set. And it seems the answer is at least like it seems the answer is either no or you need like some fundamentally new things.
Like I'm trying to understand what that composition means then, because I've like when I compose programs or functions, like there's a notion of that. I'm trying to understand what that means. Like as a what are the rules that
Yeah, so I don't think there's any meaningful way to talk about directionality. Like because like essentially all that's happening is that either your edges are present or not, right? Depending on which supply it is. So like so I mean but then once an edge is present, you can traverse it either way.
I guess in the path, you know, you went through K, like there sort of is a direction, you go along that path. from one
Right,
to the next,
but-
but you're allowed to traverse an edge in either direction.
Yeah, exactly. But I mean, effective resistance even in effective resistance computations, it's not clear whether your flow goes either way, no? Like, yeah, okay. I guess an optimal flow there would also always be like one particular direction thing. But it could be like, for instance, think of this. Like I take one input where I go where only this edge, and this edge are present. And then I take a different input where only this edge, and this edge. Right? Now, essentially, in one input I traverse this edge like this way, whereas in the other input I traverse it this way. And that's so different. And somehow there's no way to kind of enforce that you can only traverse an edge in just one direction. Somehow the framework is like it doesn't support that. And somehow also this seems to be much harder to do. Like people have tried, but it seems very clear.
Can you remind us that whether this directed graph in the ST connectivity framework?
In the
ST connectivity framework.
So in the ST connectivity framework that I'll talk about after also has only undirected.
I see.
It's really not clear how to take like
I
the ST connectivity framework and make it directed. This is somehow very weird. Like people don't
Yeah,
know.
they make sense, I think. Yeah.
Okay, anyone. Okay, so let's see. Yeah, so I already told you guys how to compute the positive witness. You just take the like you put all the positive witness sizes of the individual edges on like as resistances on the edge, and then compute the effective resistance of the resulting graph. And it turned out that for negative witness, you can do something similar. So let's say that this is our particular graph, where only P3 and P6 are positive. Then what we're going to do is we're going to contract all the nodes that are reachable from one. But here you can go from S to this node and this node, but all the other nodes are not reachable. So what I'm going to do is I'm going to contract all these nodes together. So I just contracted those three into S here. And then all the remaining edges will be negative, right? Like all the edges that remain, your input will be negative. So I'm going to put the inverse of the negative witnesses there on those edges. And then the negative witness size will be the inverse of the effective resistance of this graph. So there's a bunch of steps here. Like I don't expect you to completely remember all this, but like I just want to highlight that for both the positive and a negative witness, there's some kind of like effective resistance computation that tells you what the new witnesses are in this new stuff.
So very silly question. If there isn't a path, what will the resistance be?
So like if there isn't a path, you're in naive. right?
Oh, I
So
see.
then,
Yeah, yeah, yeah.
so,
Cool.
so then you compute the negatives.
It's almost, I see, that was.
Yeah, okay, so this is a effective resistance. And one remark that I want to make is so I now told you like what the graph composition framework does, how it kind of takes small span programs and turn them into a bigger span program. But one more thing that I should mention is that if all of these span programs that we started with, if they are all trivial span programs, so they are all just doing single bit queries, then we recover this ST connectivity graph. So that was already known before, and like this graph composition is somehow generalizing ST connectivity towards having arbitrary span programs on each of the pages.
Also, I guess in the original framework, there's also effective resistant computation.
Yes,
Yes,
right.
If we just like plug in a trivial span program in your framework.
Exactly. So then all of these will all be one.
Yeah.
But okay, they already had some weights inside, so okay, they already knew a little bit more, but this is a more generalized way of looking. Right. So this is the graph composition framework. And like the very core component here is to do all these effective resistance computations, right? And it's nice that it's like, it has like an exact characterization in terms of effective resistance. But sometimes effective resistances can be a bit cumbersome to compute. So what I do in this work is I give also like some theorem that is like a little bit weaker, but that allows you to compute these quantities a bit more easily. And this I refer to as the path cut theorem. And essentially all that I'm saying is that the positive witness size is upper bounded by the witness sizes along a path, and the negative witness size is upper bounded by the witness sizes along the cut. So let's say that this is our positive input again. What we can do is we can single out like one particular path to go from S to T. Now I'm just going to put all the positive witness sizes on that path. And now I'm just going to sum them all up. And this is going to be an upper bound on this new witness. Right. So I guess like if you remember all your effective resistance from high school, then this should be easy. Like and similarly for the negative input, if there's no path go from S to T, what you can do is you can like take a cut through the graph, put all the effective or all the negative witness sizes on those edges, and then sum them all up. And this will be an upper bound on the negative witness sizes. Right, and yeah, so this is a somewhat simpler version to like do all this witness computation. But we'll see in a bit that like it's still quite hard like, for the thing to. Any questions about this?
You've sometimes been saying witness and sometimes witness size.
Yeah, so okay, formally what I mean is like a witness is the vector and the witness size is the norm squared.
And that's the norm square, right?
Yeah, so these things are the norm squared.
Okay.
All right. So now what I propose to do is look at some examples, also to see a little bit like how this works in action. So let's do that. So I'll start with like arguably one of the easiest examples, which is the computation of the OR function using this. So how does it work? Well, the OR function is a function that only accepts whenever the Hamming weight of your input bit string is at least 1. So you're looking for is there at least the 1 thing. And if you think about like what graph you can draw where you can only go from S to T, if the Hamming weight is at least 1. Essentially what you can do is you can just take n parallel edges and put trivial transparent programs on each. Right? So I hope that it's clear you can only go from S to T if the Hamming weight is. And now what you can do is you can do some witness computation, right? You can compute all these effective resistances. So if we have a positive instant, there will be at least a 1 somewhere, which means that they're in the path, a path going from S to T. And the effective resistance on this path will simply be 1. So the witness side will be upper bounded. And on the other hand, if we have a negative instance, so let's say that we have the all 0 string, then we can cut the graph like this, and we end up cutting like n edges, each having negative witness size 1. So then we have negative witness size 10. And now what you can do then is compute like the complexity, which will be square root of. And so you see that the resultant query complexity will be square root. Right? And so what we end up doing here is we end up recovering Grover, but without knowing anything about rotations or like measurements or like all these things. Like the only thing you have to do is think about graphs. and you can recover like, some of the very old ones. So I'm hoping that this already gives you a little bit of a taste of how it works.
Do I understand correctly? Like another way of maybe getting sort of handling or would be to just have one edge from S to T and the span program on that edge. And this would work, I guess, for any function. And the span program on that edge would just be a span program that computes OR, right? Like
Right.
we sort of always do
Yes.
this, right? So this sort of formally shows that this framework like can do anything.
Exactly. So that's true. Like it's indeed true. It's like you cannot meaningfully define any like complexity measure from this framework because you can always simulate everything
Right.
trivially by just taking a span program that already does it and just put it as one edge. Yes.
So the hope is that somehow this framework will like give you a more intuitive way or sort of like give you some tools for thinking about how to design
Exactly.
other bounds on.
And hopefully in the next couple of slides, I can convince you that there is.
I mean, I guess this example already sort of shows that that's sort of what you were saying, that somehow okay.
So the reason that the square root comes up is kind of somewhat black box in the definition of C.
Yeah, so the complexity was defined as the square root of the maximum positive witness size times the maximum negative.
I see. And we didn't like deeply motivate that definition or something.
So like, well, okay, not in this talk, but it is deeply motivated by the fact that this is somehow like what the quantum algorithm needs, right? If it wants to do this detection between whether some like everything is rotating or like some part is like there, like this is somehow like the quantity that naturally shows up.
So there's something that has to.
Yeah, exactly. Yeah.
I mean, I guess you mentioned that you can rescale the positive
Right.
negative witnesses, and from this you can already see that somehow.
You need to part. Yeah. Exactly. Yeah, because
You can do the product.
yeah. Right, but then the square root is like, okay, you have to read the theorem.
Do you have like it's? I'm sorry.
Go ahead.
Like it's like present just for this going to this Grover example, that square root seems a little deep. Like, do you know why that square root is there? Like,
Well, I mean, that's a somewhat open-ended question. I like there are several different ways in which you can argue there should be a square root there somehow, but I wouldn't say I have like one very convincing definitive.
the question is like, is there some like that square root is capturing some feature of vector space of Hilbert spaces that you wouldn't have in classical combination?
Yeah.
So I'm just trying to understand if there's
I
a
suppose. Yeah, I don't think I have like a full definitive conclusive answer. Like I guess it's just somehow like quantum is like
Yeah, so you can calculate the upper bound, but can you also construct an algorithm using this framework?
Yes, actually, okay, so I didn't completely mention this, but like if you go back to the original picture, I also drew like a green line from span program to quantum algorithm. This is somehow like a somewhat more constructive way to come up with an algorithm from a span program than was previously known. So essentially, like once you know all these spaces, then you can also construct like a quantum algorithm, like really just showing what gates you have to put where, like in order to make this. I can say a little bit more about this at the end of the one.
Sure.
I have a dumb question. So yeah, so by the cut theorem, like we can estimate the negative, negative witness weight. But why is the end? I mean, like if we just check the the resistor line, the circuit is like from S to T. There are n edges, right?
Yeah.
And why isn't the resistor line 1 divided by n?
Yeah, exactly. So that's because like the negative witness size is the inverse of the.
Okay.
Of this edges all being.
I see. Sure. There's a very inverse.
Yeah. Very good. I mean, I didn't stress it much, but yeah. So you have to take the inverse. Okay. Any more questions? So like this is known to be optimal, but it's not clear from this picture.
Okay.
The lower bound proof goes through completely different. All right, so that's the OR function. Next, maybe let's have a look at an example which is a little bit more intricate than the OR function, which is the threshold function. And so what's the threshold function? Well, again, we have like n bits as input, and now I'm only going to accept whenever the Hamming weight is at least k. Right? So it's like, if you set k as 1, you get the warp function. And now what I did here is I kind of took I drew this example for when n is 4 and k is 3. So it looks already like a quite complicated construction. So maybe let's try to build some intuition for what's going on. So what you can see is that we have like 3 layers here, right, between S and T. And somehow, like in the first layer, we are somehow searching for a 1 somewhere. Okay? So here we're looking, okay, x1, 1, x2, x3, where. And now once you find a bit which is 1, so let's say x1 is 1. And in the next layer, we're looking at the remaining bits to see if one of them is 1. And if we then find one that's if we find a second one, then we look at the last 2 remaining bits to check if one of those is 1. So I'm hoping that at least from the structure of this graph, you should be able to see that you can only go from S to T if the Hamming weight is at least 3. And so, like in general, we'll have like a graph with like k layers like this, where we are searching like in this way. Right. So I hope to at least convince you that this graph indeed computes the function that we want to compute. But then, of course, the question is, okay, what are the effective resistances then of this graph? And so what you can do is like, if we take like the input 1, 1, 1, 0, it's positive instant, right? You can put like, the resistances on all the edges. And then if you do this resistance computation, you'll see that the effective resistance will be 1. We're not going to do it here because it's like tedious to do, but you can show that. And in general, like you'll find that the effective resistance size is equal. Sorry, that the positive witness size is equal to this formula here. And similarly, in the negative case, so if we take like the input x to be 1, 1, 0, 0, you'll see that there's like a cut that we can take through this graph. And then if you count up all the stuff on this cut, you'll see that the effective resistance becomes 6. Oh, sorry, the negative witness size becomes 6. And then, okay, you can compute the complexity from this. And then you can compute also the query complexity from this. And then what you will see is that this is also exactly optimal, the optimal algorithm that you get out. And so somehow, like, one thing which I think is like very, like, what sets this apart from previous constructions is that even though we get like a graph which is like exponentially big, right? If we set k equal to n over 2, we get like exponentially many edges in this graph. But still, the resulting algorithm is efficient, right? Because you get a like optimal algorithm. And like all previous approaches that took a graph and turned it into a quantum algorithm did not have that particular property. That even though your graph can become like ginormous, your resulting algorithm is still not efficient. Like at least for the specific frame, like there's examples like the GLUE3 problem where you have exponentially big graphs, but there was never like I think like a generic framework that could capture this. Right.
So this graph is not unique. You might construct different graphs.
Sure, certainly. In fact, like if you look at my PhD thesis, I have 2 different ones that compute the.
Do they give you the same answer?
Yeah, they give you the same complexity. Yeah. So in general, like these graphs, they are not unique. Like you can always do some modifications to change them without changing the weights sizes. Like, I guess if you take any edge and you were to duplicate it, right? So just put a vertex in the middle and put the same span program on both edges, and then take like half the weight on both of them, you will get like the exact same analysis. So there's always like some kind of like trivial modifications you can do without like changing it.
Sorry, it's not obvious, but how did you derive the graph in the first place?
It's like you don't want to like a lot of coding, like some kind of like because also there's weights here and so on, right? So like there was some kind of like playing with that. At some point, I had some like sci-fi optimizations.
Oh, those weights have to be fine-tuned, right? That those one.
Yeah, exactly.
Yeah.
But in the paper, I show exactly
To balance the geometric mean between positive witness size and negative size.
But I mean, the formula is very direct. Like it's some fraction between k and n.
Okay.
Or k.
Okay, got it.
But in the paper, you can find exactly what you mean. Right. So this is the threshold function. And there's one more thing I want to say here, is that this construction also works for something a little bit more general than the threshold function, which is known as the gap majority problem. So the gap majority problem only accepts whenever the Hamming weight is at least 2n/3 and rejects when, like, you're promised that either your Hamming weight is at least 2n/3 or less than n/3. So there's like some gap in the middle where you're promised that you're not there, right? And so if you now take k equals n/2, right? So we take this like ginormous graph with exponentially many edges, and we evaluate what happens on the gap majority function, we'll see that the resulting complexity actually becomes just 1 or constant. It's not 1, but like 6. And so like what that means is we can like, even though we have like a super ginormous graph, it will be able to recover constant query complexity on the gap majority function. So I'm gonna make that note here and it will come back. Okay, so this is a threshold function. Now, the last thing that I want to do is I want to talk a little bit about how you can take classical algorithms and turn these into instances to this ST-connectivity. Right, so essentially, if we have a classical algorithm, how can we build a graph, like ST-connectivity graph, that is evaluable? And so let's first start with a deterministic algorithm. So if we have a deterministic query algorithm, what we can do is we can always write this as a decision. Right, so here is like a deterministic algorithm that computes the OR function, right? Like the first query x1, if the output is 1, we go here, if the output is 0, we go here, which refers to the tree like that. Once we reach a leaf, then that's what we have. Now, what I'm claiming is that there is a generic way to turn this into a ST-connectivity problem. And so the idea is to prune all of the leaves that are 0. So I'm just gonna, forget about all of those. And then all the leaves that are 1, I'm gonna merge them together into the target node T. And now I'm hoping that it's like that you can that you guys can see that you can only go from S to T if you kind of trace like along what the decision tree would have done as well. Right. So this is how you can take a decision tree and turn it into an instance of the ST-connectivity. And now if we look at the witness size as well, the length of the path to go from S to T will of course be at most like the depth of the decision tree. So that's the analysis that we recover. And for the negative witness size, maybe we need to think a little bit harder. But at every node that we traverse in order to get to a leaf that is 0, there's exactly one edge that we're not taking. Right. And so a cut through this graph would just cut through all the edges that you are not taking at every node. So that's also going to be at most the depth. Number of edges that you need to cut. And so then what you get is that the resulting complexity is indeed upper bounded by the depth of the tree and hence by the deterministic query complexity. Right, so every deterministic algorithm can be turned into a ST-connectivity. But then the question is, okay, we know how this works for deterministic algorithms. Can we also do it for randomized algorithms? And this, like for the longest time, I had no idea what to do, but actually like 2 or 3 weeks ago, I figured out how this works. So what you do is the following. What is a randomized algorithm? Well, you take, like, a randomized algorithm is just a bunch of decision trees with an associated probability distribution. So you're going to take one of the decision trees at random and then evaluate them. And now what I want to claim is that without loss of generality, you can assume that this probability distribution is uniform. Right? Because if the probability distribution is not uniform, you can just duplicate a bunch of the trees in your set, make your set a little bit bigger, and then like have the probability distribution be. But then once you assume it like this, essentially all you end up doing is computing the gap majority function on your set of decision trees, right? Because once your probability distribution is uniform, then in the positive case, more than 2/3 of them will accept, whereas in the negative case, less than 1/3 of them will accept. And so now what I want to do is I want to take all of these constructions, right? All of these ST-connectivity constructions, and put them as edges in this gap majority construction that we saw before. Right? So we take this ginormous graph, like exponentially many edges, and each of these edges we're gonna, like, instead of having this edge, you put like this thing like as whole block on that particular edge. Right? So you make like a super big like ST-connectivity graph. But then like you can only go from S to T if the algorithm makes sense. And then if you do the analysis, you'll see that like the resulting complexities, they multiply. So you get like the one from the gap majority analysis, and you get like the depth from the from the deterministic decision trees. So this is how you can show like how the randomized algorithms fit into this ST connectivity flow. Any questions about this?
Can I have a question about that notation? So what is the 2t, like what's, even earlier you had 2x2.
Yeah, so this 2 is the scalar multiplication, right? So it's like this rescaling of the initials.
Oh, I see, I see.
Right. So you need to add this to kind of like these initial factors here, the scalar multiplication factor, they allow you to kind of play a little bit with like what happens in this witness computation, like so the computation of the witness size. They are kind of like parameters you can tune to make sure.
Remind me, why do you bother doing?
To like, so if you were to put one here everywhere, like you would not grayscale up, then like your effective resistance would not be like, your resulting effective resistances would change as well.
Yes.
Right. And then you'll see that if you take their product, then it's not going to be optimal.
Oh, I see. Oh, that's nice.
So somehow there's two things you can do. Not only come up with like a good structure for your graph, but also you have to play a little bit with the weights to make sure that your effective resistance computations will be efficient.
Sorry, I think that maybe I missed it. Like, is the claim there you can always do this? Or a given graph, like you can always find the weighting to make it efficient? That's the.
In general, once you fix the graph structure, it's not so clear what the optimal weights would be. It's kind of hard to figure that out.
Okay, but
Is
in
that
this
what you want
case,
to know?
it just works. Sorry.
Sorry?
In this case, it just works.
Yeah, in this case, it just works. Yes. Like in general, it's a hard problem, like to figure out like exactly what weights to put in. At least, or okay, I shouldn't say it's a hard problem, but at least I don't know how to. Like, so. All right. Well, in view of time, I think like I had one more example, but I think we're gonna skip over this. And I'm just gonna summarize like what I've been talking about. So the first thing I did is I showed you guys this picture, like showcasing a little bit how what I did like fits into the bigger landscape of things. Yeah, and there's one thing I wanted to say that I forgot to say earlier, which is that like I think this is the first time that we actually in some kind of like meaningful way figure out how like randomized algorithms fit in to any of these frameworks somehow. Like because like before, like there was like some randomized version of this decision tree framework, but it was all somehow like constructed to fit like what randomized algorithms are somehow. But here, like ST connectivity, we really didn't do anything to the framework, right? We just showed that randomized algorithms just fit in it, like and there's no modifications. So that's somehow what I'm very excited about it. Yeah. So okay, so this is what I talked about. Yeah, so we had to look at span programs, we had to look at what graph composition is, we had to look at a bunch of examples from ST connectivity, and then I showed you how randomized algorithms fit with that. And then I just want to quickly highlight that in the paper there's more things that I haven't covered today. So one thing is related to the question that we had earlier, which is like once you have one of these graphs, like can you then kind of like implement the resulting algorithm time efficiently? So I do some effort in the work to try to figure out like how you can do this. And there's something interesting there is that like if you are able to put a description of your graph into some efficiently addressable memory, so you put it in some QRAM or so, it can help a lot for like efficient implementation of these algorithms. So I think like it is not really like, yeah, it depends if you want to kind of assume that like QRAM is a thing or not. but if QRAM ever becomes a thing, then I would say that all of these things can also like there's at least like a bunch of things you can do to implement these things.
But does it like require exponential memory? QRAM exponential memory.
No, just well, if your graph is exponential size, then perhaps yes. Yeah. Like, but I would say linear in the size of the graph. Yeah, but the graph can be exponential. So but I mean it's also not definitive, like maybe there's even something better you can do than if your graph is efficiently computed. Right, so that's one thing I wanted to say. Then the next is that, like, so I mainly been talking about what was going on, like in the first paper that I put on archive. In the second paper, I tried to kind of like take this overview of the different like algorithmic frameworks, and also expand it to like the quantum walk framework. So there's a whole world out there of quantum walk frameworks that I haven't covered here. So in the second paper, I'm trying to do like some kind of generalization of this to quantum walks, which if you guys want, I could also talk for another hour about. So like, but yeah, so always feel free to come to me and we can have a chat about that. And then finally, there's a bunch more examples in the paper you can see. And I would like to end with like the biggest open question that I still have. And actually, I should say there's like two open questions that I still have. Like, and they're both related to this ST connectivity framework. So, like, we now know that ST connectivity sits in between randomized algorithms and quantum algorithms, right? But so for some of these partial Boolean functions, we know that quantum algorithms can do like much better than randomized algorithms, right? I think there's this like correlation problem or so where we know that like randomized algorithms need like polynomial number of queries, whereas quantum algorithms can do it in just one query. And one thing I would like to know is whether you can find such separations between quantum algorithms and ST connectivity, or between ST connectivity and randomized algorithms. And for both of these relations, I have no idea like how to prove like a separation between them. And it's tantalizing because at least one of the two has to be true, right? Because we know already there's like some kind of a separation between quantum algorithms and randomized algorithms. So for relation, ST connectivity must be either constant or non-constant. But even that, like I have no idea. So yeah, there's like some kind of open problem there where I've been hitting a wall. So if in any of the coming 2.5 weeks, like any of you would have to would like to think about that, I'd be more than happy to give it some. And I think the crucial question here is like, can you in some way argue give some kind of argument saying you can never do something in ST connectivity graph? So can you give some kind of lower bound? Like, okay, if you had some graph that computed this function, then it has to have this complexity. So such kind of argument I'm looking for, but I have not. Okay, so yeah, I think that's one to say. Thank you so much for being here.
We have a lot of questions during the talk, but maybe we have time for a few more questions if there are some.
Just me, right?
Yeah.
So I guess for both span programs and for these graph composition algorithms, you use the same sort of complexity metric you defined at the beginning in terms of the sizes of the positive and the negative weights, which sort of looks to me like a kind of a worst case measure.
Yes.
So if I want to understand, you know, something average case, like let's say I'm happy with an algorithm that succeeds with constant probability for a random instance, can I just define a different complexity metrics and use the positive and negative weights to figure that out? Or do I have to do more work with the framework?
It's a good question.
I think so.
Yeah, there should be something you can do, like, but it's not directly clear what it will be. Like, I think one thing you can do is like say, if you take the worst case negative width size, so you take the maximum of all the negative witnesses, then you can recognize whether something is a positive witness in time, the positive witness of that actual input times the worst case negative witness times. So you can do something like if you have a positive input, you can certify this in time, which is proportional to just that witness size times the worst case negative witness. And once you have that, then you can build this into like a average case statement as well, saying that, okay, if the average witness size of my positive instances is small, then also this procedure should succeed with high probability. And then there's symmetry between positive and negative witnesses, so you can play the same game on the other side. Yeah, okay, so I guess there's something you can do, but I don't think like people have done it in the literature.
Yeah, I have some comments. So for span program, it's actually a metaphor to to the case where you are consenting about like the worst case or no worst case input, but like a average case input. Yeah, like the framework itself is can do this, but you need to do like change your complexity measure. Like currently, the complexity measure is like square root of like a worst case positive witness size and times worst case, negative witness size. Yeah, like you need to change that. Like if I recall correctly, you just change it to like an average, the average size of like the two, and you. But maybe it's more difficult than that, complicated than that, but it's definitely doable. Then you just rerun the whole argument Arjan presented here, and I don't see any clear obstacle. So in principle, you can do that. Yeah.
Yeah. You can definitely change one of the two to be an average. I'm not sure about both. Maybe I haven't given it much thought, so maybe we know more. But
I have any questions. Can we go to the last page?
the last bit.
Yeah. So I have two questions. I don't know why it's like, why is the error from randomized algorithm not pointing directly to graph composition? It seems like your reduction is using like graph composition, not ST conductivity.
Oh, well, no, because let's see. Like here, if you take like this is really ST conductivity.
Oh, okay.
Because we're doing just trivial span programs on each edge.
Oh, you embed this
Exactly. So you take this whole graph. And you take S and T to be the two vertices.
I see.
Right. So you take the whole graph and just put it in here.
Makes sense. Okay.
And that way you build like really a true ST conductivity.
Okay. Makes sense. So second question is like for if so your framework basically combines span programs to build a new span program, right? Is it possible such that if I replace each span program by an actual quantum algorithm, time efficient, can your framework produce a time efficient algorithm after like this composition?
So if the algorithms are exact, then yes.
Okay.
But the problem with these kind of things is that usually your quantum algorithms have some bounded error.
Yeah.
Things, right? And so the point is that if you have these errors happening in these algorithms themselves, then if you start composing them, these errors they kind of build up in the composition.
But there's a recent work like showing that for relatively trivial case, you can like remove those like low factors.
Yeah, right. So like,
can that be used in your framework?
I mean, I would not be surprised that there is some kind of crossover that you can do this. But you would necessarily have to change something in the construction because like the thing about span programs is they really exactly capture, function computation, right? Like there's this really exact condition whether W0 can be written as the sum of these two things.
Sure.
And somehow it's not clear to me at least how from like an arbitrary quantum algorithm you get to such a setting where you have such an exact condition.
So one obstacle is that maybe like it's not easy to even give a bound because your graph can be exponentially large or doubly exponentially.
Yeah. I don't know, but this is certainly an interesting question.
Yeah, because like if that works, then basically we get a completely new way to like build new quantum algorithms from like established quantum algorithm,
right,
and it's time efficient.
Right. Yeah, so yeah, would certainly be interesting, but like I think it sounds deceptively simple to do, but I think there's some stuff that's just not so clear what Any more questions?
Okay, well, maybe that's a good place to wrap up, but we're just around for another 2.5 weeks, so there's maybe more time for discussion offline, but let's thank him again for a really beautiful talk.